Well, hello, good people. Today we are talking about ramps and inclined planes. This is part 2 of our lesson on 2D force vectors. We started by looking at things where you had something like a box and then some force was being applied to that box at an angle like this, and you had to break that down into its x components and its y components to fit in with the other forces that were acting on that box. Well, today we're going to look at not if the force is being directed at an angle, but what if the box itself is on an angle, which is what we see in ramps and inclined plane problems. We are going to start today by drawing a few free body diagrams, and I am going to start by making my eraser enormous. Okay, yay, so that I can erase this box here that I drew. Why did you even draw it if you were just going to erase it, Ms. Wilson? I don't know, man. It just happened. Okay, let's start by drawing a free body diagram of a tomato sitting on the ground. Here is the ground. And here is a tomato. Wait for it. It's going to look great. Oh gosh, I really did just nail that, didn't I? So just my tendency is to nail things. Okay, let's suppose that you had a tomato. No, not that, please. Thank you. Let's suppose that you had a tomato like this one. And, oh gosh, I don't like the stem. Sorry, I'm taking it back. And let's suppose that you, oh no, it's giving me the working symbol of death. Let's suppose that you shoved the tomato to the right side of the screen. So you shove it this way. And then the tomato starts to slide and slow down. If you wanted to draw a free body diagram of a tomato sliding and then slowing down, you would say, okay, well, that tomato is experiencing a force due to gravity that is pulling it down. Then that tomato is also experiencing a normal force in the opposite direction here, and that is holding up the tomato. Then you would say the weight and the normal force should be equal in length here because the floor is going to push up on the tomato just as hard as the tomato is pushing down on the floor. And I would say, great, so true. And then if I said, hey, if this tomato is sliding this way, what other forces would you draw as it slides and gradually slows to a stop? A lot of students want to say there's an applied force going this way, but that is not correct. There is an applied force as long as you're pushing the tomato. But once your hands are off the tomato, there's actually no force being there's actually no force being applied to the tomato in that direction once you've let go of it. Now, is there an applied force to get it going? Yes. But is there an applied force to keep it going? No. So all you need to draw here is not the applied force, but the only other force that's acting on this tomato right now is, oh no, my arrow showing the direction of motion. The only other force acting on the tomato right now is the force of friction. I will call this Fk because this is kinetic friction and not static friction. The last thing I would do with this free body diagram is I would definitely, most certainly define my axes. I would most likely call this way positive y in the up direction because that makes sense to my brain. And I'd most likely call this way positive x because that's the way that the tomato is going. Now, if you wanted to call this way positive x, then that would also be totally great. You could also call down positive y if you want to. Any of those options are totally great and awesome, but you would need to define your axes some way. That is a tomato on a hill. Or that is a tomato on a flat ground. Let's draw a tomato on a slight slope. Here is a tomato on a slight slope. Can you draw a free body diagram of a tomato on a slight slope? I'm gonna add some colors to my tomato. Yeah. Okay, well, that is a lot of greenery, but I think it's gonna work for us. Okay. Now that the tomato is on a ramp, Let's suppose that this tomato just slides down the ramp. Let's ignore rolling for now. We won't actually do any rolling today. If you really want to do rolling, please come hang out with us in AP Physics, where you will learn all about rolling tomatoes. But for today, let's just say that this tomato is sliding down the ramp. Could you identify the three forces that would be happening to this tomato? Well, you say, yeah, sure, Miss Wilson. If this tomato is sliding down the ramp, then gravity would be acting on it. The normal force would also be acting on it because the normal force is happening on the ramp. And lastly, the force of friction would be slowing it down. And I would say, all of those things are true. You are so brilliant. Let's talk about the directions of each of those forces. First, the force of gravity, oh gosh, let me try that just one more time. The force of gravity is going to pull straight down towards the earth like this. A lot of students, once they start drawing ramps, will try to draw the force of gravity going different ways. Like they'll draw the force of gravity going this way, or they'll draw the force of gravity going this way. Or this way. But let's be very clear. Gravity does not care whether or not you are on a ramp. If you are on a ramp, gravity pulls you straight down towards the center of the earth. If you are on the floor, gravity pulls you straight down towards the center of the earth. If you are standing on the wall, gravity pulls you straight down towards the center of the earth. It doesn't matter what your ramp looks like. Gravity will always, always, always pull straight down, regardless of where you are. So we draw the tomato and we draw the force of gravity pulling straight down. Then let's talk about the normal force. The normal force will always act perpendicular to the surface that is creating it. That's why it's called the normal force. You'll remember that normal in math class means perpendicular. And so it is going to be perpendicular to the surface. The surface here, this is a little side diagram. The surface here can only shove the tomato this way. The surface could not shove the tomato like this way. I can kind of show you with my hands here. It maybe makes more sense with my hands. Okay. If I had a tomato, pretend this eraser is a tomato. If I had a tomato sitting on my hand like this, and I were to give that tomato in the my hand, we're giving a normal force. Do you see how that normal force has to be going this way? Then the ramp has to be shoving the tomato this way. It wouldn't be able to shove the tomato straight up. Well, I'm not showing this very well, but it wouldn't be able to shove the tomato straight up like this because the ramp is at an angle. So the ramp will create a force that is perpendicular to the surface of the ramp. Right now, my ramp is shoving the tomato up at an angle like this. So when we draw the normal force, we draw it perpendicular to the ramp. Let me go ahead and erase these. Okay. So our normal force will go up perpendicular to the ramp like this. And there's my normal force. And lastly, let me label it. Okay, lastly, there would be a force of friction, and because this tomato is sliding down the ramp, it would be a force of kinetic friction. This force of kinetic friction is going to be parallel to the ramp because it's going to be between the bottom of the tomato and the surface of the ramp. So it's going to be right along that line here. Friction is not going to shove the tomato back this way at a straight line like this. No, because that's not the way that the surface of the tomato and the surface of the ramp are in contact with each other. Instead, it'll go this way. So there is our FK. Okay. Before we move on, check and make sure that the direction of all of these arrows makes sense to you. What we're going to do next is we're going to talk about the magnitude or the length of each of these arrows. Now, I haven't drawn them the correct lengths yet because I want to talk a little bit about how we know the correct lengths. We'll start by drawing an axis that we will define. When it comes to ramps, I have found that it is easiest for students to call down the ramp positive x and perpendicular to the ramp positive y. This strikes some students as very strange because why is my y terrible? Well, that's how you draw y, right? Why does mine look so bad? It just looks so awkward and goofy. I'm so sorry. I am very sorry. I just want it to look like a Y. Okay. This strikes a lot of students as strange because they are used to this way being X and up and down being Y like this. But let me show you why this is going to be very convenient. Do you see how when I label my axis this way, I have the normal force is all in the y direction. There's none of the normal force that's in the x direction. Do you see how Fk is all in the negative x direction? There is no part of Fk that's in the y direction. The only force then that's in the x and the y direction is Fg. Fg has a component that is parallel to the ramp, a part of it that is in the x direction, and a component perpendicular to the ramp, a part of it that's in the y direction. What we do when we define our axes this way is we make it so that there's only one force that's in two directions instead of before when there were two forces that were in two directions. So it makes our math quite a bit simpler. Let's go ahead and take a look at the lengths of each of these vectors. The first thing that we are going to do when we take a look at each of these, the length of each of these vectors, is we have to look at, we have to look at the x and y components of the weight. Gravity is pulling straight down, but there is a component of this gravity that is perpendicular to the ramp like this. And there is also a component of this gravity that is pulling the tomato straight down, perpendicular to the ramp like this. So there's a component that's parallel and there's a component that's perpendicular. We call the component that is parallel like this FGX because it's the part of FG, sorry, that looks really crowded there. It's the part of FG that is in the x direction, and we call this part FGY because it's part of the weight that's in the y direction. You have experienced this before. If you are sitting on a hill, there is not suddenly a magic ramp force or a hill force or a sloped force that makes you go down the hill. What makes you go down the hill? Gravity. Gravity pulls you down. It's because there is a part of your weight that, or your weight has a component to it that is parallel to the ramp or parallel to the slope or parallel to the inclined plane. There's also a component of your weight or a part of your weight that is perpendicular to the inclined plane or perpendicular to the ramp. We call this one FGX and we call this one FGY. This one pulls the tomato down the ramp and this one keeps the tomato on the ramp so that the tomato doesn't float off of the ramp. When we look at our free body diagrams, Fn should be the same size as Fgy. Notice how this tomato is not accelerating in the y direction. It's not flying up into the sky and it's not plummeting down towards the center of the earth. So when we draw Fn, we need to draw the length of Fn to reflect this truth or this reality that the tomato is not accelerating in the y direction. If the tomato is not accelerating in the y direction, that means that the up forces have to cancel with the down forces. My up force here is the normal force, and that has to cancel out with the y component of the weight. The y component of the weight sticks it to the ramp, and the normal force keeps it from going through the ramp. So these two will cancel each other out, and they'll be equal in size. Let's talk about the size of FGX and FK. If we look at the size of these two vectors here, you'll see that right now FGX is less than FK. Can you think about for a second, what does that mean for the tomato's motion? Hey, did you say that this tomato is currently slowing down because FK is greater than FGX? And so if it's sliding down the ramp, then it would be slowing down since the friction would be winning out over its weight? Because that's what you should have said. If you wanted to show that this tomato was not slowing down, but was in fact speeding up, the way that we would show this tomato speeding up is you would have to have, you would have to have an FGX that is greater in size than FK. FK would have to be less than FGX. And if you wanted this tomato traveling at a constant velocity means no acceleration in the x direction, which would mean that FGX is equal in size to FK. So, you can see here a few things. First, that this normal force has to be equal in size to FGY because the ups and downs have to cancel out. If you have constant velocity, then the x component of the weight has to cancel out with the force of friction. If it's slowing down, the force of friction wins over the force of gravity. And if it's speeding up, then the force of gravity in the x direction wins over the force of friction. Let's try drawing one more. Yeah, actually, we'll draw two more. Fine, okay. Suppose that this tomato then went on an even steeper slope like this. And once again, our little tomato is going to slide. Can you try right now, before I finish it, can you draw a free body diagram in your notes of the tomato as it slides down the ramp? And, sorry, yes, I am going to make my tomato a little bit smaller for the sake of consistency. Okay. Go ahead and draw a free body diagram while I get my colors out and draw a tomato. I don't like that very much. Okay, that's pretty. I mean, that's not terrible. It could be worse. Yep. Oh, it could be a lot worse. It could also be a lot better. I still think my favorite tomato is the first one. That one just looks sublime. Okay. You said, Miss Wilson, at this point, I'm a pro. You say, I drew the weight going straight down. And I say, yes, of course you did. Because you know, except that that's not straight down. Because you know that the weight does not care about the fact that this tomato is on a ramp. Gravity does not care at all. And gravity says, nope, I will be exactly the same here as I was before. And I will pull this tomato straight down towards the center of the earth. Very good. Then you say, okay, this weight has two components to it, and you definitely most assuredly defined which way you want to call positive y and positive x. You said this tomato has an x component to its weight, like this here. When you draw this, a lot of students like to say that the x component due to gravity, when they're first drawing this diagrams, they'll say something like, yes, and here is the x component of the weight, and they draw it like this. Hey, why is that super, super bad? Because gravity never pulls the tomato up a ramp. Gravity only ever pulls down a ramp. So you will only ever draw gravity pulling down a ramp. You will never draw gravity pulling up a ramp. If you are drawing gravity pulling up a ramp, then you are drawing the world wrong. So try that again. First, we draw the x component of gravity pulling down the ramp. You'll notice here that we always use dotted lines. The reason why we always use dotted lines is because this is not a real force. This is a part of gravity. It is not a force in and of itself. For us, solid lines mean that it's a real distinctive force. A dotted line means that it's a part of a force. So we have a part of a force here. A lot of students will draw something like this. They'll draw the x component like this. And then they'll draw the y component. Whoops, I'm doing this very bad. So sorry. Let me just try that again. They'll draw the y component looking something like this. Can you figure out why is that bad? The reason why that's bad is because this is in the x direction here, but do you see that this is not in the y direction? The y direction is perpendicular to the ramp like this. Do you see how this line right here is not perpendicular to the ramp? So that is not a good drawing for the y direction. Instead, we would draw the x direction, and I'm nervous about my undo button here, because sometimes if I do it too much, then it gives me the working wheel of death, and that means that it's like game over forever. What we do is we draw the x direction this way like this. Then we draw the y direction down so that the y direction line, or the line for the y component of the weight is going to end up, and I'm just drawing this very, very badly. Let me try. Okay, there we go. That's much better. The y component of the weight should be nice and perpendicular to this ramp here. Do you see how the y component of the weight is perpendicular to the ramp? And the x component here of FG and the y component here of FGY, they should make a very, very nice 90-degree angle right here. So that's how I know that I did it right. We'll label this as FGX. We'll label this as FGY. Now, wow, except that I can't write G apparently. Okay, now we have the normal force. The normal force needs to be, and I'm feeling all like self-conscious about the way that I drew my FGX. I just don't love it. Okay. Now, the normal force needs to be equal in size to FGY. Notice, the normal force when the tomato is sitting flat on the counter, the normal force has to cancel out all of the weight. But here the normal force doesn't have to cancel out all of the weight, it just has to cancel out the y component of the weight. And lastly, we draw the force of friction. Let's suppose that this tomato is accelerating down the ramp. If the tomato is accelerating down the ramp, then I would have to draw my Fk as being less in length to Fgx. Okay, now let us take a quick pause here. Before we move on, I want you to see if you can answer these questions. As we go from flat to steeper and steeper and steeper, as we increase our slope size, what happens to Fg for increasing slopes? What happens to Fgx as our slopes increase? What happens to Fgy as our slopes increase? What happens to Fn as our slopes increase? And finally, what happens to Fk as our slopes increase? As you go through each of these, I want you to say, does it increase, decrease, or stay the same? Go ahead and pause the video, take a second, think about it, and take a look at your little pictures and use your logical brains. Okay, here's what you should be saying. First, for Fg, and I did not well represent this in my diagrams here, so you would say, bad Miss Wilson, you did a terrible job with your tomato pictures. I'm so sorry. As you look at my slopes increasing, Fg should stay the same the whole time. Remember, gravity does not care if you are on a slope, and it does not care if you are on the floor, and it does not care if you are on the wall. How hard the earth pulls on you is always going to be the same. It's always going to pull on you with Fg. You are not going to weigh less or more if you get on a ramp. Otherwise, ramps would be America's greatest weight loss program. You could make tons of money selling ramps in America. But that is not the case. A ramp does not change the size of Fg. Fg will always be the same for an object, and it will always be pointing straight down. What it does do when you put something on a ramp is you change how much of the weight is pulling down the ramp and how much of the weight is pushing into the ramp. As a ramp gets steeper and steeper and steeper, more and more of the weight is pointed in the x direction down the ramp, and less of the weight is pointing in the y direction into the ramp. You know that this is true from your life experience because you know that a steeper downhill is scarier on your skis. Why? Because as it gets steeper, more of your weight pulls in the x direction and less of your weight is pulling your skis towards the hill. This means that the net force on you will be greater and you will accelerate much faster. Then, check out the normal force. The normal force always has to counteract Fgy. So, as the ramp gets steeper and steeper and steeper, and Fgy gets less and less and less, the normal force gets less and less and less. And finally, Fk. This one is not as intuitive, but here's what you know, is you know that Fk is equal to mu k Fn. If, as these ramps are getting steeper and steeper and steeper, Fn is decreasing because the ramp doesn't have to overcome all of your weight, it just has to overcome Fgy, and Fgy is getting smaller and smaller and smaller, so the normal force is getting smaller and smaller and smaller. If the normal force is getting smaller and smaller and smaller, then the force of friction, Fk, is also getting smaller and smaller and smaller. This is another reason why a steeper hill is scarier on your skis, is because not only is more of your weight going to be pulling you down the hill and directed in the x direction instead of keeping your skis on the hill, but also the force of friction is getting less and less and less because the normal force is getting less and less and less. Let's say that now we took the tomato to ultimate levels, and let's say that we took our ramp and we made it so steep that it looked something like this. And we put the tomato on our ramp. And we said, here you go, little tomato, have a nice time sliding down. And we put, wow, my tomato looks squished. It's not squished yet. Okay, 1 second. Put the tomato here. Okay, perfect. And now let's give it little leaves. Can you draw a free body diagram of the tomato in this situation? That's not terrible. It could be worse, but it could be better. Here's what you're saying. You're saying in this situation, gravity is pulling this tomato. Whoa, I am in the way. That is embarrassing. Okay, gravity is pulling this tomato straight down towards the center of the earth, which is true. If I asked you how much of this force due to gravity is pulling the tomato down the slope now, you would say, well, all of it. If I asked you how much of it is now going into the slope, you would say, well, none of it. So if I asked you what the normal force is, you would say there's no normal force. And if I asked you what the force of friction is, you would say there's no friction. There's nothing that is pressing the tomato up against the cliff, and there is no friction because there's no normal force. And with no normal force, you have no friction. So this tomato at this point would be in free fall. Do you see how as you get steeper and steeper and steeper, FG always stays the same, but more and more and more of the weight is pointed down the ramp until at its steepest at 90 degrees, all of the weight is pointed down the ramp. And do you see how as the ramp gets steeper and steeper and steeper, less and less and less of the weight is pulling you towards the ramp, or towards the floor, basically towards the inclined plane. Less and less and less is keeping this tomato planted on the ramp until here none of the weight is keeping it planted on the ramp. You also see the normal force getting smaller and smaller and smaller. Well, here the normal force would be 0, and you see that the force of friction would get less and less and less until here it's 0. And that, ladies and gents, is a little bit on ramps and inclined planes. And that is all for today, folks. I do hope that you have a wonderful rest of your day, and I will see you all in our next video or in class. Yay. Bye, good people.